welcome to Easy BTech, your guide for BTech and beyond. In this channel, you can learn the subject very easily. My name is G. Sampath. I am going to explain the subject VLSI design. Today we are going to discuss the driving large capacitive loads. Driving large capacitive loads. Driving large capacitive loads. Large capacitive loads. So when it required large capacitive loads, large capacitive loads are required. Large capacitive loads required. Large capacitive loads required. So on-chip capacitance to off-chip capacitance. When it drive, large capacitive loads required on-chip to off-chip. On-chip to off-chip. On-chip to off-chip drive. Off-chip driving. Right? What is on-chip? On-chip means within the chip. On-chip. On-chip is within the chip. Within the chip. Right? Within the chip. So off-chip means beyond the chip. Beyond the chip. Beyond the chip. Outside the chip. Beyond the chip. So when we are driving within the chip to outside the chip, then there is a large capacitive loads required. It should maintain from on chip to off chip. In order to drive the off chip, on chip should maintain the large capacitive loads. Off chip capacitance is off chip off chip load capacitance. Let's say off chip load capacitance. Off chip load capacitance is several times greater than on chip capacitance. Greater than on chip capacitance. On chip capacitance. Right? Off chip load capacitance is several times greater than the on chip capacitance. So on chip should maintain, that's why on chip should maintain large capacitive loads. Large capacitive loads in order to drive off chip capacitance. Off-chip capacitance. So on-chip capacitance should maintain the large capacitive loads in order to drive the off-chip capacitance, because off-chip capacitance is several times greater than the on-chip capacitance. Off-chip capacitance, off-chip capacitance, off-chip capacitance is load capacitance is several times greater than or equal to 10 power 4 square Cg. Okay, square Cg is the unit of the capacitance. Now it will be 10 power 4 times than the square Cg value, load capacitance of the off-chip capacitance. In order to drive this load capacitance of off-chip, on-chip should maintain the large capacitive loads in order to drive this 10 power 4 square Cg. In order to drive this off-chip capacitance loads, it should maintain the on-chip this much 10 power 4 square Cg. More than this, then it will be drive the off-chip capacitance. So in this, there is a possibility of cascade connections, cascade connections of inverters. So the possibility of maintaining on-chip capacitive loads increase in order to drive the off-chip capacitance. So there is a cascading connections of inverter, so that the on-chip capacitance, load capacitance should be increased. Let us see the cascading connections of inverter. Let us see this cascading connections of inverter. Yeah, this is a diagram of cascading connections of inverter. Increase the size of inverter so that it will be maintain the large capacitive loads, right? Large capacitive loads. You see, this is one inverter, this is one inverter, this is another inverter, and this is another inverter. Like, okay. So here we are maintaining the length and width ratio 4 by 1, 1 by 1. And the second inverter maintaining the length and width ratio 4 by 1 and F, and 1 is to F. So this parameter, width parameter, is increasing. Now this one is 4F square, 1F square, right? So the finally here the maintaining the you can see this one more, maintaining the load capacitance, right? Here maintaining the load capacitance, increasing the load capacitance. You see in the cascading connections, the jet pull up pull down ratio maintaining. So cascading connections of inverter, cascade connections of inverters are cascading connections, cascading connections of inverters. By using this cascading connections of inverter, then cascading connection of inverters maintain the, let us see this one, inverters maintain large capacitive loads, maintain large capacitive loads, large capacitive loads, right? Maintain the large capacitive loads, and the each inverter By using these cascading connections, then large capacitive loads is maintained in on chip. So it will be each inverter, each inverter having pull up pull down ratio, jet pull up by jet pull down, jet pull up by jet pull down. This will be equal to L is to W ratio. We can say it is L by W. And say it is jet pull up, jet pull down, jet pull up, jet pull down, jet pull up, jet pull down. L is to W, L is to W ratio, L is to W ratio. Now in this, it is NMOS inverter. It is NMOS inverter. It is NMOS. It is NMOS inverter. It is NMOS inverter cascading connection. It is NMOS inverter cascading connection. Cascading connection. Right? NMOS inverter cascading connections. Where L is the L is to W, where L is length of the channel, length of the channel, length of the channel. W is width of the polysilicon, width of the polysilicon, width of the polysilicon. Right? Length cannot be changed. Here length of the channel cannot be changed. Channel length cannot be changed. Channel length cannot be changed. Cannot be changed. It is a fixed feature size. Cannot be changed. It is a fixed feature size. It is a fixed size. It is a fixed size according to design. According to design. According to design, it is a fixed. Right? So width can be changed. Width can be changed. Width can change. So width of the polysilicon, W, width parameter, width parameter can change. Width parameter can change in order to maintain large capacitive loads. Maintain large capacitive loads. Large capacitive loads. Right? Large capacitive loads. One thing is increasing large capacitive loads. Increasing large capacitive loads. Large capacitive loads. Increasing large capacitive loads should reduce resistance. Right? Should reduce resistance. Should reduce resistance. Resistance in the inverters. Resistance in the inverters. Right? In the inverters. So we know resistance R is equal to the formula resistance R is equal to RS into L by W, where RS is the standard sheet resistance. RS is the standard sheet resistance. Standard sheet resistance. Standard sheet resistance. Standard sheet resistance. L is the length of the channel. Length of the channel. Length of the channel. Right. W is the width of the gate. Width of the gate. Width of the gate. Right. Width of the gate. So increasing or decreasing resistance. If you want to decrease the resistance, reduce the resistance. If you reduce the resistance in the inverters, reducing the resistance, then what happens? Reducing resistance in the inverters, load capacitance increased. So load capacitance increased. Load capacitance increased. Load capacitance increase. Load capacitance increase. So reduce the resistance, then capacitance increase. Then what is the resistance in the inverters? R is equal to formula R is equal to RS into L by W. L is the length of the channel, W is the width of the gate. Right, reducing the resistance, then capacitance increase. Right, only the width parameter is increased. That's why if you see here, that's why the width parameter, F is a width parameter. This parameter is increased. This parameter is increased. So resistance reducing, resistance reduce, capacitance increased. Resistance reduced, capacitance increased. Capacitance increase. So then we can maintain the large capacitive loads across the output terminal, right? Cascading connections of inverters should maintain the large capacitive loads. So each inverter having the pull-up pull-down ratio L is to W, right? This one is L is to W. L is the length of the channel, W is the width of the polysilicon. So length cannot be changed, it is a fixed size. It is a fixed size in each design. In each design it is a fixed size. Width parameter can be changed. You see, only width parameter L is to W, width parameter is changed F and F square, right? Width parameter is increased. We know that R is equal to RS into L by W, right? From this, resistance is reducing, width parameter is increased. Width parameter is increased. If width parameter is increased, it should be maintained the large capacitive loads, so that it can be drive the on chip to off chip, on chip to off chip, right? So resistance reduced, capacitance increased. Resistance reduced, capacitance increased, right? That is a possibility of maintaining on chip driving large capacitive loads. Now let us see the time delay calculations. Time delay calculations. Time delay. Time delay of time delay of inverter. Time delay of inverter. Time delay of inverter. Time delay of inverters. Cascading connection. Inverters in cascading connection. Inverters in cascading connection. Cascading connection, right? What happens? Then what is the time delay? What is the time delay inverter to inverter? Width parameter is increased. Now let us see this one. Now let us see this one. Here F is a width parameter. F is the width parameter, right? N is the number of connections. N is number of connections, number of cascading connections. Number of cascading connections. Number of cascading connections, right? N is the number of cascading connections. F is a width parameter. So time delay per gate. Time delay per gate. Time delay per gate. So time delay per gate is equal to F into tau for delta V in. So delta V in and 4F tau 4F tau for del V in, right? So this one is delta V in is increasing logic 0 to 1. It is 0 to 1. It is 0 to 1 input V in. Okay, and this one is del V in is 1 to 0. It is 1 to 0. It is 1 to 0 as a input to the inverter. V in to the inverter. V in to the inverter. Right? V in to the inverter. So last class we discussed that NMOS inverter cascading connection. When 0 to 1 is given, it is a on transistor. It is a on transistor. It is off transistor. Okay, so it is 0 to 1 is on transistor. On transistor resistance 1 tau, on transistor 1 tau, and 4 tau is off transistor. So 1 to 0 means enhancement mode transistor is off. So we call it is off transistor. It is off transistor. Off transistor. Right? Off transistor. We are seen in the last class. So 5T, 5 tau is the 5 tau is a 5 tau is a NMOS inverter pair delay. NMOS inverter, NMOS inverter, NMOS inverter pair delay. NMOS inverter pair delay it is. Each inverter to inverter pair delay is NMOS inverter pair delay. So 5 tau. Tau is a delay unit, nanoseconds. If 7 tau is the CMOS inverter pair delay. Inverter, CMOS inverter, CMOS inverter pair delay. CMOS inverter pair delay. Right? Last class we discussed CMOS inverter delay and NMOS inverter delay. So CMOS inverter pair delay is 7 tau and total one inverter to another inverter. 5 tau is the NMOS inverter pair delay. Right? So time delay produce, let us take time delay produced by the two inverters. Time delay produced by inverters, produced by inverter NMOS and CMOS, NMOS and CMOS, NMOS and CMOS. Y is equal to load capacitance CL by square CG. This will be equal to F power N. Right? F power N. F is the width parameter, N is a cascading connections, number of cascading connections, right? F is a parameter, F is a width parameter, F is a width parameter, right? F is a width parameter, N is a cascading, number of cascading connections, number of cascading connections, number of cascading connections, right? Cascading connections, number of cascading connections. So F and F increases, N decreases, increases, F increased, width increase, then number of cascading connections are decreased. F increased, N decreased, N decreased. So both are interdependent. F and N are both are interdependent, right? Interdependent. Now, if you apply the reducing the n parameter, applying the natural logarithm of both, so for exponential values, we can apply natural logarithm. ln y is equal to logarithm of f power n. So from this, the number of cascading connections n is equal to ln y by the ratio of ln f, right? So number of cascading connections, number of cascading connections, cascading connections, cascading connections, number of cascading connections, number of cascading connections, number of cascading connections n is equal to ln y by ln f, where y is the number of time delay produced. So total time delay produced, y is equal to for both NMOS and CMOS, f power n. F is the width parameter, n is the number of cascading connections, right? And if n is equal to even number, n is even number of cascading inverters, even number of inverters. So the formula is n by 2 phi f tau. This will be equal to, so 2.5 nf tau for nMOS, for nMOS. This is for nMOS. So for nMOS, the number of cascading connections are even number of inverters are there. So n by 2 phi f tau is equal to 2.5 nf tau. It is for nMOS, right? If it will be n by 3 7f tau, this will be equal to 3.5 nf tau, right? F is the width parameter, n is the cascading connections, right? Tau is the units, right? CMOS, this is for CMOS. Okay, so for all the cases, for all the case, so we can take time delay. So delay is directly proportional to n into f tau, where n is equal to natural logarithm of ln y by ln f into f into tau, right? Where f is the right, f is the cascading connections, tau is the time delay. So this is about time delay calculations. If inverters are using even number, right? NMOS. And if even number of cascading connections of inverters in CMOS, 3.5 n tau, 2.5 n tau. If any all the cases, delay is directly proportional to the n into f of tau. So natural logarithm y by ln f, right? This one is the cascading connections of inverter time delay calculations, and how it will be increase the load capacitance on chip to off chip by increasing the width parameter. Length parameter cannot be changed, it will be fixed size in a design. So width only we can change. So width is a parameter, we can reduce, we can increase the width. What happens, resistance reduce. So capacitance over here, capacitance, the overall capacitance is increased. So from on chip to off chip, the on chip capacitance should be increased, so that it can easily drive to the off chip capacitance, right? This is about driving large capacitive loads. Driving large capacitive loads should maintain the large capacitive loads by increasing the width, increasing the width and reducing the resistance. Each cascading connections of inverter is possible to reducing the resistance, right? Time delay calculations also we are seeing this NMOS inverter and CMOS inverter and total time delay. Okay, so please subscribe our channel, inform to your friends, please like. Okay, so learn the subject very easily, right? Thank you.